Today we're going to introduce something new called oxidation numbers. Okay? And oxidation numbers are similar to charges, but they're not always exactly like charges. Okay? So I need you to read read the paragraph on page 232 having to do with oxidation numbers. Okay, just to give you a brief introduction as to what they are, what we use them for, and then we'll talk a little bit about how to find them.
232?
Page 232, yes. What oxidation numbers are used for is they tell us kind of the charge or the distribution of electrons around a particular atom. Okay, so the overall charge of a molecule tells us how electrons are distributed throughout the entire molecule. But these oxidation numbers kind of help us just tell us where the electrons are distributed by a particular atom or surrounding a particular atom. So that's what oxidation numbers are used for. Okay, and in order to kind of look at our oxidation numbers of elements within a compound, we have specific rules that we have to follow. Okay, like always. Everything in chemistry I feel like has rules. So I'm going to give you the main sets of rules that we're going to follow here for oxidation numbers, and then we'll just get in and start doing some practice because I think it makes more sense once we start looking at actual practice problems. Okay, so I'm just going to start giving you the rules, okay? They're outlined on page 232 as well, but I'm going to give you kind of the abbreviated versions of that, okay? So first of all, when we're looking at assigning oxidation numbers, these are typically given within a balanced chemical equation, okay? Within a balanced reaction is what we're looking at here. But when we assign these, we're looking at individual atoms, okay? So within a compound, we look at atoms and we assign oxidation numbers to a specific atom, okay? An overall compound does not have an oxidation number. It has a charge, okay? Individual atoms within a compound have an oxidation number. So when we're looking at that, if we find an element by itself within a chemical reaction, like sodium or like oxygen or anything by itself, anything that's elemental, that's not a compound, so elemental atoms, they have an oxidation number of 0. Okay, so there's elemental atoms. If an atom is by itself or an element is by itself, it's got an elemental or it's got an oxidation number of 0. Okay, that's because it's a neutral atom. Those electrons are distributed evenly. Okay. Our next rule is that we're going to look at some specific examples with elements. Okay, and our rules from here on out is when we're looking at a chemical compound or a chemical formula. Okay, so these are when they're bonded to something else. Fluorine always has an oxidation number of -1. -1. Okay? It always gets to keep its -1 charge as its oxidation number. That's just how it works. So fluorine always is a -1 oxidation number. That's the same as its charge, right? Because fluorine's in group 7, it has a -1 charge. It gets to keep it. Okay. Our next rule or example that we have to follow is for oxygen. Okay, oxygen, most of the time or almost always, has a -2 oxidation number. There's only one exception to this rule, and the only exception is when it's bonded to fluorine. Okay, that's the only exception. Then it becomes a +2. Okay, because fluorine takes precedence. Fluorine always gets to keep its -1 charge, so when oxygen would be bonded to fluorine, oxygen would then have to switch to a -2 because those electrons would be located closer to fluorine than to oxygen. And that's what our oxidation number is kind of representing, is where those electrons are kind of shading to. Okay, our last element here that we're going to look at that has a specific rule is hydrogen. So hydrogen has an oxidation number of +1. Okay, it's always a +1 if it's paired with an anion or with a non-metal. If it's paired with a metal, then it's -1. Okay, but we don't really pair hydrogen with metals often, so you won't really have to worry about that. More often than not, hydrogen will be a +1. Okay, it'll keep its charge. So hydrogen, oxygen, and fluorine are the ones that we're really concerned about that have specific rules. Okay, so hydrogen most of the time is going to be +1, oxygen most of the time will be -2, and fluorine most of the time will be -1. Okay, those are our kind of 3 for sures. All right, so on top of that, we have rules that the rest of the elements have to follow because we have other elements that we use to make chemical compounds. So does everyone have what they need to up here? Okay. Rules for keeping, well, I guess first of all, do you guys understand how electronegativity works on the periodic table? Have you talked about electronegativity before? Okay. So when you look at the periodic table, if you don't have your periodic table out, I would suggest that you get it out. Okay, so I'm going to give you our next rule, and then we're going to talk about it. So it's okay if you don't quite understand what it means right now. Okay, so our next rule is that the most electronegative atom or element, I'll put element so that makes more sense. Most electronegative element, which will always be an anion, gets to keep its charge. Okay, so when we're assigning oxidation numbers, we're going to look at the most electronegative anion, and they will get to keep its charge as its oxidation number. So now I'm going to talk to you just briefly about what electronegativity means. Okay, electronegativity means how badly an element wants electrons. Okay, how badly they want to draw electrons to them. So the way that electronegativity works on the periodic table is that fluorine is the most electronegative atom on the periodic table. Fluorine wants electrons more than any other atom on the periodic table at all. Okay, fluorine will take electrons from anything and anyone. Okay, why do you think that is? Do you have an idea as to why that might be? Think about how many energy levels it has, and think about how many valence electrons it has. Right? It's its energy level closest to the nucleus. That's where all electrons want to be, is close to the nucleus. And it also has 7 electrons, so all it needs is 1 more to complete its shell. So fluorine will take electrons from anything. Okay, so from there, electronegativity decreases as you move down and to the left. So francium, which is the farthest to the down and left, will give up electrons to anything. Okay, it doesn't even care. It doesn't want them. So as you look at electronegativity, it starts with fluorine and decreases as you move down and to the left. Okay, so when we're looking at electronegativity or which ones might get to keep its charge, things like chlorine will keep its charge, oxygen will keep its charge, sulfur, bromine, these atoms right up here near fluorine will tend to get to keep their charge as their oxidation number. Okay, so that's what that rule means, that electronegativity increases as we're near fluorine. So these nonmetals up here on the right-hand corner will typically get to keep their charge as their oxidation number. Okay, and the metals kind of have to work around that. Okay. I think this will make more sense once we start doing problems, but I have to get the rules out there so that we can work with them. Okay. Oxidation numbers must add up to 0 in a neutral atom. Okay, so just like the charges that we've been working with balancing charges for these binary compounds so that they have an overall neutral. We do the same thing with oxidation numbers, okay? If the atom or if the molecule or the compound has no overall charge, that means we need to get the oxidation numbers to have an overall neutral, to have a 0, okay? So same with charges, we're going to have some positives, some negatives within our compounds. We have to get those to equal 0 if the overall charge of the compound is 0, all right? And it works the same way if the molecule has a charge. Okay, so oxidation numbers must add up to the charge of an ion. Okay? So we know that ions are any compounds that have a charge, or any element or atom or compounds that have a charge, right? Remember the term ion? Yeah, no? Okay, anything that has a charge is considered an ion. So these oxidation numbers have to add up to that charge if the overall compound has a charge. Okay, so if we have a -1, that means we need to have our oxidation numbers add up to -1. Okay, does that part make sense? Okay. So those are our rules for oxidation numbers. I know it seems like a lot, but this is kind of a long-winded way of balancing charges like we've been doing. Okay, so we're going to do some examples. The book, we're going to do the examples that are in the book, so if you want to follow along, you can. We're just going to do we're going to do them in class like we always do. Okay, so the examples are on page 233 and 234 if you want to check or follow along with them, but we're going to do them all together as a class anyway. So when you assign oxidation numbers, you assign them for each element in the compound. Okay, so you have to assign them for all elements. You won't just typically pick one, you'll assign them for all. So the first element we're going to look at here is UF6. Can anyone name that molecule? Uranium's in the actinide series, I'll give you that. Good. Okay. So let's go ahead and assign oxidation numbers. Okay, if we follow our rules, what do we know the oxidation of fluorine always is? It's -1, okay? I'll go ahead and write these in a different color so it's a little easier to see. So fluorine has a -1 oxidation number for a single fluorine atom. How many fluorine atoms do we have here? 6. That means the overall on this side has to be -6 because we have 6 of those -1 fluorines. So what does that mean that uranium's oxidation number must equal to have a neutral atom? Yes, +6. That means uranium's oxidation number is +6. Fluorine's oxidation number is -1. That's it. That's all we're doing here, is working backwards from an overall charge to kind of give those oxidation numbers for each atom.
Now, will the first element of every compound be the same as the charge of, say it was F negative F5 or not F5 but F5? Would the UV +5?
Yep, we need this to overall be equal as 0. So we need this positive plus the negative to equal 0. Okay, since this UF molecule has no charge overall, it's not a negative or a positive, then we need those to equal 0. So yes, the positives should always equal the negatives. All right? So that was the easy one. Let's look at H2SO4. Can anyone name that compound? Okay. No. Hydrogens are bonded first, so that gives us a clue that it's an acid. Okay? So if it's an acid, we look at what our anion is here. What's this molecule right here? Sulfate. So it's called sulfuric acid. Okay? Okay, so let's follow our rules here to assign oxidation numbers. We have two of them here that we can follow. What do we know oxygen's oxidation number is usually, or always? Oxygen is usually -2. Okay, oxygen is -2, hydrogen is +1. Let's try this one. This is a polyatomic ion, and it has the name of chlorate. Good, chlorate. ClO3- is chlorate. So we want to assign oxidation numbers. How many elements are we even dealing with here? 2. Chlorine, which is Cl, not Ci, Cl, and we're dealing with oxygen. Okay, this time, the only difference that we have this time is that we have this negative charge here that we're dealing with. Okay, so that means our oxidation numbers are going to add up to what? Our oxidation numbers should add up to -1. They should not add up to 0. Okay, so oxygen's oxidation number is always -2. And we have 3 of those, which gives us a what? -6. And we want this bottom part to equal -1. Okay, we know we want to equal -1 because the overall charge on the molecule is -1. So we know our oxidation numbers have to equal -1. So what will give us a -1 if we have a -6 and some positive number here? Yeah, +5. Okay, so that means chlorine's oxidation number here is +5. Okay. Is that a charge that chlorine normally takes on? No. Okay? And it's hard to tell between oxygen and chlorine which would be more electronegative, right? Which would get to keep it. Typically what you do is if there's 2 anions together, you take the one on the right side. That gets to keep it. Okay? Oxygen will win out over chlorine every time. All right? So then if we label our answer, we say chlorine equals +5, oxygen equals -2. Okay, oxygen's oxidation number is not -6 here. It's -2. All right. Okay, let's do a couple more. Look at okay. Just because the molecule is bigger doesn't mean our process gets any different. Okay? We still have oxygen and we have phosphorus. Between those two, which one are we sure of?
Oxygen.
Yeah, we're sure that oxygen is going to keep its -2. Okay, so oxygen gets its -2, and if we have 10 of those, that means our total down here at the bottom might be what? Yeah, -20. Does this molecule have an overall charge of any kind? Do you see an overall charge? So that means we need these oxidation numbers to equal 0. We need them to add up to equal 0. So that means if we have 4 of these phosphorus molecules, what should the oxidation number be if we want this bottom to be +20? We need it to be +5. Okay? We know this because we need it to equal +20. There's 4 of them, so we just take 20 divided by 4 there to get our +5. Okay? So our answer then would be phosphorus equals +5, oxygen equals -2. Okay, what questions do you have?
What if it was like P3?
Helium, or hydrogen, I mean. We'll try one without our big 3. Okay, this is called germanium chloride. Germanium is a metal, chloride is a non-metal, so we name it with our ionic rules. Which of these 2 compounds is closer to fluorine? Chlorine. Okay, so chlorine gets to keep its normal charge, and what's chlorine's regular charge? minus 1, okay? Minus 1. That means overall we have a negative what charge down here? Negative 2, because we have 2 of those chlorine or chloride ions. We want the overall here to equal what? 0, because there's no charge on germanium chloride. It's a neutral atom, so that means we need it to equal 0 overall. So that means what do we need to have germanium's oxidation number be equal to? Plus 2. Very good. We need it to be plus 2 down here. Since there's only one of them, that gives us germanium as a plus 2. Good, so we would say germanium equals plus 2, chlorine equals negative 1. Okay, feel confident with oxidation numbers?